Differential calculus isn't just theory on a chalkboard. Derivatives are the perfect tool for solving real problems and making the best possible decision. Today we'll explore one of its most elegant and practical applications: optimization. Have you ever wondered how to design the perfect can? We'll use derivatives to optimize its dimensions, saving the maximum amount of material possible. Imagine a cylinder. It has a radius at its base, which we'll call r, and a height, which we'll call h. If we unfold the can, its total area, A of r, h, is the sum of the two circular lids, 2 pi r squared, plus the rectangular body, 2 pi r h. To manufacture it, the volume V must stay constant. This lets us solve for the height h as V over pi r squared. By substituting h, we get the area function depending on a single variable. Take a look at this beautiful equation. To find the value that minimizes this area, we calculate its derivative. A prime of r equals 4 pi r minus 2v over r squared. We set the derivative equal to 0 to find the critical point. Simplifying, the volume V must equal 2 pi r cubed. Substituting the volume back in, we get the perfect design. The height h must be exactly equal to 2r. In other words, equal to the diameter. Let's see it graphically. On the left, we plot the can's area, and on the right, the behavior of its derivative. As we vary the radius r, watch how the slope of the tangent line changes. As we shrink the radius and approach the lowest point of the area, the derivative becomes exactly 0. This is where the optimal design happens. Slope equal to 0. We've found the absolute minimum point for manufacturing our can using the least possible material. Let's compare 3 designs with identical volume. A tall, narrow can uses too much surface area. A very flat can requires even more material, making it inefficient for the manufacturer. However, our optimal mathematical design minimizes the area to its absolute limit, flawless savings, and a mathematically perfect can.